Hi everybody, I hope this video finds you well. In today's video, we're going to be further investigating mathematical proofs by looking at our second proof technique, which is called a proof by contrapositive. So in today's video, we're going to discuss a little bit about exactly what a proof by contrapositive is, what is the contrapositive. We're going to talk about a little bit of sort of just logical understanding of this idea, and then we're going to look at some examples of writing out mathematically a proof by contrapositive. So let's start by what a proof by contrapositive is. Well, we can see right here that a proof by contrapositive is a mathematical proof where we directly prove the contrapositive of a given conditional statement. So a couple things to keep in mind here. A contrapositive proof is basically one where we prove a different but logically equivalent statement to the one that we are initially trying to prove. That does mean that the actual work of a contrapositive proof is still done in the manner of a direct proof, meaning that once we change the statement from its original format to its contrapositive, we will then conduct a direct proof, just like we saw in the past, where we proceed from our given assumptions through a series of steps to our desired conclusion. The big difference here, though, is that we're not going to prove our original statement in the form that we encounter it in. Instead, we're going to prove the logically equivalent contrapositive. This idea of the contrapositive works when you have a conditional statement, which basically means if we have sort of an if-then type of statement that we are trying to prove. So let's start off by talking a little bit about exactly what the contrapositive is. Logically, the contrapositive means that if we have a statement written as P implies Q, the contrapositive of the statement is that not Q implies not P. So in words, right, this is how we would write this logically. We use that little symbol here, sort of written like that to indicate not. In words, we would just read that as not Q implies not P. Now, what's really important here is to realize that this contrapositive is logically equivalent to the original statement. That means that if P implies Q is true, if that is a true statement, then not Q implying not P is also a true statement. It also means vice versa. If not Q implies not P is a true statement, then P implies Q is a true statement. So if one of them is true, the other is true. We're going to be imagining that we're presented with something like this, but since we don't want to proceed with a direct proof of this statement, we will instead do a direct proof of the contrapositive, this statement, not Q implies not P, and once we've completed that proof, that will ensure us that even though we prove the contrapositive, P implies Q is also true. Now, one thing to just keep in mind when you're thinking about the contrapositive, you can sort of think about the contrapositive as negating both statements and reversing the order of the implication. So you'll notice here that P implies Q becomes not Q. So P was originally first, now Q is, but we've negated it. And then not P is second. So you're negating the statements and reversing the order of the implication. Now, a couple quick notes before we look at sort of just like a little basic example of the contrapositive, right? The contrapositive is very different than the converse. The converse is simply reversing the order of a statement. So the converse of P implies Q is Q implies P. That's just reversing the order of the implication. Those two statements are not logically equivalent. So there are situations where P implies Q is true, but Q implies P is not true, and vice versa. So we never are going to be using the converse when we're trying to do this proof by contrapositive. They are not logically equivalent, so if we end up proving the converse, we get no information about our original statement. So we have to make sure to focus on proving the contrapositive. Also, as a note, in terms of identification, early on in terms of your sort of career in mathematical proofwriting, it is probably more important to simply understand how to approach, how to logically think about, and how to write down proofs of each of these different styles. But in the long run, you also will want to sort of have a good idea about how to identify when you should do a direct proof, when you should do a proof by contrapositive, or when you should do one of the later types of proofs we're going to talk about, like proof by contradiction or proof by mathematical induction. So here's a quick note that might help you a little bit with that identification. The contrapositive is a proof technique that should be used only when proving conditional statements. So you really want to reserve this for when you see something where you have an if-then type of statement. That's because we can get the contrapositive of that sort of if-then format, as we talked about here, right? If P, then Q. Well, we know the contrapositive is not if not Q, then not P. It is also, and this is more from a usefulness side, it is useful to use a contrapositive when the negation of the components of the statement, the P and the Q, are easier to work with than the original statements. It might not be immediately clear what we mean by more useful, but as we do a couple examples here, we'll sort of make note about how, when we do this, the negation of the statements becomes a little bit easier to work with than the original statement. Now, before we get to our mathematical examples, we're going to do two of those in just a few moments, but let's first just have sort of a little example logically based on a simple statement to understand the contrapositive. So here is an example of a statement that, we can probably sort of assume here is true, right? Maybe I say something like I tell you, if I eat a whole pizza, then I will feel full. That is a conditional statement telling you that if I happen to eat a full pizza, then I will feel full. So in this case, we would be in our sort of notation here, we would be imagining the statement of P is eat a whole pizza, and then Q is the statement feel, misspelling a little bit there, feel full. And of course, this statement here then would just simply be P implies Q. If I eat a whole pizza, then I will feel full. Now, the contrapositive of that statement is saying if I do not feel full, then I did not eat a whole pizza. So notice that the contrapositive here is not Q, which is do not feel full. And the negation of the statement P is did not eat a whole pizza. And then notice that the contrapositive of our statement is that not Q implies not P. If I did not feel full, then I know I did not eat a whole pizza, right? And you can see why these are logically equivalent. We're basically saying if you eat this giant pizza, then you will feel full. If you know that you're not feeling full, then you know you didn't eat that whole pizza, because if you did, you would feel full. They are logically equivalent statements. Now, let's look at the converse, which is not logically equivalent. Notice that this says, if I feel full, then I ate a whole pizza. And if you think about that, it should just sort of by common sense clearly not be the same type of statement, and probably for most of us wouldn't be true. There's lots of other ways that we might feel full. Maybe we ate a bunch of some other food, right? Then we could feel full, but we didn't necessarily eat that whole pizza. So in this case, right, the statements are Q, which is feel full, and P, which is eat a whole pizza. They're the same statements as what we had up there, but this would be Q implies P. The order has been reversed. That's the order of the implication has been reversed. And this is not logically equivalent. These two are logically equivalent. And again, just from like a common sense perspective, you can sort of see why this example makes sense. I think we would all agree that if we eat a whole pizza, then you'll feel full. That would also mean that if you're not feeling full, you didn't eat a whole pizza. Those are equivalent statements. But this one doesn't really make sense. If you feel full, it isn't necessarily true that you ate a whole pizza, right? That's a different type of statement. So this one is not logically equivalent. So we got to be very careful about separating the contrapositive from the converse. For the remainder of this video, we'll always be talking about the contrapositive. You might ask yourself, where does the converse appear in mathematics? Well, sometimes we will prove if and only if statements in mathematics, where we want to show that P implies Q is true and Q implies P is true. Basically, both directions are true. Then we often talk about the converse because what we'll need to do is we'll need to prove the original statement and we'll need to prove the converse. We'll need to prove two separate statements. But the converse will never help us prove the original statement, which right now is our goal. So we'll be focused on the contrapositive. Okay, let's look at some examples of using the contrapositive. So here's our first example. This is going to be something sort of similar to one of the proofs that we did in our sort of discussion of direct proof. It's going to be a proof about trying to show something about the parity of different numbers. So this says we're going to prove that if n squared is even, if the square of a number is even, then the original number n is even. Now, when we do this, right, well, let's imagine, I mean, we're talking about a video here about contrapositive, so most likely we're going to use the contrapositive for this, but let's imagine we first start with an attempt at a direct proof, right, since that's what we had talked about in the past. And we'll see, as we start to do this direct proof, why it's not really going to be super easy, and it's not necessarily impossible, but it's not going to be super easy to proceed with the direct proof, and why we might want to try something like the contrapositive. So we're going to be trying a direct proof here. We're sort of assuming n squared is even, and we know what that means, right? That tells us that there exists some k, an element of the integers, such that n squared is 2k. Okay, and we need to show that n is even. So that tells us that we need to show that there exists some other element of the integers, m, an element of integers, such that n is 2m. Okay, so now if we imagine actually starting our proof, the first thing we would do is we'd probably go ahead, just like we did in our other direct proofs, think about what do we have as known knowledge, what do we have as assumptions, and we'd say, well, we're assuming that n squared is even, so we might start with n squared equals 2k, and then we somehow have to arrive here, but since we're working with integers, it's not going to be clear how we're going to move from n squared to n. You might say, well, we could just use the square root, but then we're going to arrive at something like the square root of 2k, and that doesn't look anything like what we're trying to do here. I mean, then we're introducing radicals, potentially we're introducing an irrational value. That doesn't really seem like there's going to be an easy way to proceed from here to something that looks like 2 times an integer, right? Just the simple introduction of that square root is going to make things pretty challenging. So we seem to sort of be stuck. So that could mean that we just maybe have to think a little bit more or try to be a little bit more clever with our logical steps or our mathematical operations, but instead, let's try a proof by contrapositive. So let's instead try a contrapositive here. So in our original language, right, we'll use a little bit of color to make this clearer, right, this if here, right, p is the n squared is even, and this, right, is our q, right? N is even. And we're trying to prove that p, well, maybe switch this back, implies q. That was our original goal. So let's actually apply the contrapositive. So the contrapositive here, right, if we do that, the contrapositive would be that we would need to prove that not q implies not p. Okay, so we need to prove that not q implies not p. So let's write down what those statements would be. Well, not q would be n is not even. Now that doesn't sound great initially because like something being not something else often doesn't give us a lot of information. But luckily with integers, if you're not even, right, well, that immediately tells us n is odd, right? If you're not even, then you have to be odd. For integers, every integer is either even or odd. Also notice that it's not too bad when we negate p, right? Not p means that we need to show n squared is not even, which implies that n squared is odd. So what we're going to be doing now is we're going to be assuming that n is odd. And of course, what that means, as we know, is that there exists a k element of the integers such that n equals 2k plus 1. You could also use 2k minus 1, but I think we used in the past 2k plus 1. So we know that there exists an integer such that n equals 2k plus 1. And we need to show that n squared is odd. So that means we need to show that there exists m, an element of the integers, such that n squared equals 2m plus 1. Okay, so let's actually start our proof then. Once again, we'll start with our initial assumption that n is odd. So for our proof, we'll have n equals 2k plus 1. And notice we're in a lot better of a spot here. Because if we look back at the direct proof, we sort of didn't know how to proceed from here to here, right? Because we'd have to introduce that square root. But here, proceeding from n to n squared is easier. We can square both sides, and that doesn't introduce an operation that we don't really know how it's going to interact very nicely with our integers. So let's do that. We can square both sides. That means n squared is 2k plus 1 squared. And now we can do the mathematical operation of actually expanding out that square. That's going to be 4k squared plus 4k plus 1. And remember, our goal is to get to something that looks like that. So we can notice that we can factor a 2 out of the first two things. So 2 times 2k squared plus 2k plus 1. And then this is what we can call our m. So we can go ahead and just say something like let m equal 2k squared plus 2k. And then we have our n squared is 2m plus 1. Notice that that is exactly what we needed to show. And we are all good. Now, what we have done is we have technically shown that if n is odd, then n squared is odd. So we have proven, right, just as a sort of comment here, we proved that if n is odd, then n squared is odd. But like we talked about, this was the contrapositive of our original statement, so that also means our original statement must be true. So also, if n squared is even, then n is even. So this part here, I wouldn't really say is necessarily necessary when writing like a formal mathematical proof. This is more just to comment that we prove the contrapositive, and that means that the original statement is also true. I would say that if you wrote all this sort of stuff out here, where you actually sort of said, I'm using the contrapositive, I'm going to assume this, I would need to show this, and then you showed that, I would say most people would be comfortable understanding what you've done there, so you don't really need this comment. But again, just for our sort of first example here, we're showing that we prove this statement, and then that is logically equivalent to the original conditional statement we wanted to prove. So there we go, right? There's an example of our contrapositive. Now you might ask yourself on this, why was this one a good one for the contrapositive? And again, part of the reason is you could just say, well, if you try a direct proof, you sort of get stuck. But another, maybe slightly more intuitive way is to sort of think about that if we look at how this original if-then is formatted, we're being given information about the more complicated term and then trying to make a deduction about the simpler term. And that's sort of backwards from how we normally think about things. We normally like to get information about the simple thing and then deduce something about the more complicated one. So it was convenient when we did the contrapositive that we then had information about the simpler thing, that n was going to be not even, and then we knew that that actually meant that it had to be odd. That was also really useful. And then we had to deduce something about the more complicated n squared. So that was a sort of a signal that the contrapositive might be useful. It also was a good sign that the contrapositive was going to work, that statements like being even is easy to negate, right? If you're going to use the contrapositive, you're going to have to know how to negate the statements. And considering that the negation of being even is being odd, it was convenient to work that way, so we were in good shape to use our contrapositive. Let's look at a second example that actually comes from a famous result from calculus. So, for our second example, we're going to have a sub n be a sequence, and we're going to prove that if the limit of that sequence doesn't equal 0, then the infinite series summing up the terms of that sequence automatically diverges. Now, for some of you guys, if you're seeing this sort of series of videos before you might have taken Calc 2, you might not have really encountered sequences or series too much. That's okay. I think that this explanation will still generally sort of make sense about what we're sort of doing here. Hopefully you've at least seen the concept of a limit before, and you should be comfortable with this. For some of you who've maybe already done some Calc 2, you'll recognize this result here as what we call the test for divergence. It's one of the first things you learn for diagnosing the behavior of an infinite series. And it basically says that if the limit of the terms isn't 0, then the series automatically diverges. Now, I'm not going to go through and write out the attempt at a direct proof, but I want you to sort of see why this one is not a great candidate for a direct proof and why the contrapositive is probably better. If we do a direct proof, then we have to work from this assumption and try to arrive here. But if we work from this assumption, our assumption will be that the limit doesn't equal 0. That'll be it. That'll be our only assumption. We'll literally only be assuming that the limit isn't 0. We won't know what the limit is. Maybe it equals 1, maybe it equals 100, maybe it equals -5, or even worse, it might not even exist. All of those are situations where it's not 0. So the assumption that the limit isn't 0 doesn't really give us a lot of information. It tells us very little. So that makes it pretty hard to proceed forward. If we think about what the contrapositive is going to look like, though, we're going to reverse these statements. Okay, that may or may not be helpful, but we're going to negate the statements. The negation of this is, instead of being not equal to, it's going to become equal to 0. Well, that's going to be a tremendously simple statement, right? The limit has to be equal to 0. And what about the negation of this? Well, the negation of diverge is converge. And even, if you're a little rusty on your limits, remember converging means that the limit exists, and diverging means that the limit might be infinity, negative infinity, it might not exist. Once again, diverge is a very open-ended statement, but converge is a much more grounded statement, so it'll be a lot easier to work with. So let's go ahead and try that, right? So we're going to label this here as our statement P, and this guy here as our statement Q. So we're going to take our contrapositive. So our contrapositive here is going to be that not Q is supposed to imply, let's go over here, our not P. So what we're going to do is we're going to get to assume that the sum from n equals 1 to infinity of a sub n does not diverge. And what this really means is this is the same as the sum n equals 1 to infinity a sub n converges, right? When we're talking about limits in infinite series, if something doesn't diverge, then it converges. There's only two options, converge, diverge. So the opposite of diverging is converging, okay? And then what we need to show is we need to show that, well, now it's our not P, right? The limit as n goes to infinity of a sub n is not 0. So that means we need to show that the limit of a sub n equals 0. That is the negation of statement P. So we're going to assume that the infinite sum converges, and we need to show then that the limit of the terms equals 0. Okay, let's actually attempt our direct proof now of the contrapositive. So remember, format-wise, the contrapositive proofs are written like direct proofs. It's just that you're proceeding from not Q to not P instead of from P to Q. Okay, so we're going to assume, right, that the sum n equals 1 to infinity, a sub n converges. Now, we do need a little bit of knowledge about infinite series here. A lot of times when we talk about infinite series, we use what's called partial sum notation. So we're going to let S sub k equal the sum from n equals 1 up to k of a sub n. Now, that is our partial sum here. So just as a note, in case it's been a little while since you've seen this stuff, the sum from n equals 1 to infinity of a sub n is the same as the limit as k goes to infinity of s sub k. So this is just an equivalence between writing it as an infinite series and writing it in this partial sum notation. Okay, now, since we know that this converges, since the sum n equals 1 to infinity of a sub n converges, then we know limit k goes to infinity s sub k must equal some limit, right? That's the definition of what it means to converge. The limit has to actually equal some value. So we know the limit of those partial sums has to equal some actual value. We have no idea what that value is. Could be positive, could be negative, whatever, but it does have to actually equal a value. Okay, now, if we look at this, right, we can make the following sort of realization about the connection between the infinite series and the sequence. Because remember, our goal is to arrive at something like this. So what we can sort of note here is we can note this relation, right? So we can note that Sn, if we're thinking about, maybe we can use Sk, I don't think it really matters, let's use Sk. Sk is equal to S sub k minus 1 plus A sub k. This is the definition of how partial sums are built. If you want the next value in your sum, you take the original sum and you add the next term. So this is how, and again, if you haven't done infinite series for a little while, this might be a little sort of hazy, but again, this is just how an infinite sum works, right? You're saying that this next term of the infinite series is the previous sum plus the next term of the sequence. Well, now let's rearrange this a little bit. Remember, our goal, always useful to look back at our goal. Our goal is to understand the limit of the sequence. So let's isolate the sequence on one side. So I'll rearrange. We can write this as A sub k equals S sub k minus S sub k minus 1. Right? That's just by bringing this guy over and then sort of just flipping the sides of the equality so we can read it left to right. Now, let's take the limit on both sides as k goes to infinity. Okay. So, we've got that. So again, mathematical operation, right? Remember, your steps in a proof are going to be either steps of logic or steps of mathematical operation. So we're looking at the limit here. Now here, a limit, provided that we know that it converges, which we do, we can go ahead and distribute that limit, right? The limit of a difference or the limit of a sum is the sum of the limits or the differences of the limits. So we can write this as the limit as k goes to infinity, s sub k, minus the limit as k goes to infinity, s sub k minus 1. And now, remember that this we know equals L, and this here, well, even though this says k minus 1, in other words, it's one index behind, k is going to infinity. So this is headed the same place as this, and they are both going to L. So we have the limit as k goes to infinity, a sub k, which is L minus L. They're both headed based on this to L. And then we only have one last thing to do, just subtract. Limit k goes to infinity, a sub k equals 0. Is that what we were trying to show? Well, we look back up here. Our goal was to show that the limit, well, we had it up here as n to infinity, but it doesn't matter what letter you're sort of using, n to infinity, k to infinity. It's just acting as an index. This is the equivalent statement, and we've done it. We've shown that if the series converges, then the limit must be 0. And while that is a different statement to what we were originally proving or wanting to prove, it is logically equivalent to saying that if the limit isn't 0, then the series automatically diverges. So this is an example of using the proof by contrapositive, and hopefully, even if this sort of steps in here are a little unclear, maybe because it's been a while since you've seen series, or maybe you've never seen series before, hopefully the idea of why we chose to do proof by contrapositive here is clear. Knowing that the limit isn't 0 doesn't tell us much. Trying to show something diverges can mean a lot of things. It can mean infinity, negative infinity, not existing. But the negations of the statements were a lot more grounded. The negation of Q was that it actually would converge, which means it does have a limit. That's a lot of information. And the negation of not equal to 0, which was the negation of P, literally meant that the limit did have to be 0. So the negations were easier statements to work with, and that's why we use the contrapositive. In our next video, we'll be exploring another proof technique, which is proof by contradiction, somewhat similar to the contrapositive proof, but in some ways actually a little broader in scope.